right, so this video is on topics 6.2 and 6.3, which we went over on Tuesday. What was that date? Tuesday the 15th. So first thing we're going to define is angular acceleration. Angular acceleration has the symbol alpha. It's a Greek letter. And the unit for angular acceleration is a radian per second squared. And the definition of angular acceleration is the change in angular velocity over time. So kind of like regular acceleration, we're just throwing an angular term in there. So angular acceleration is the change in angular velocity over change in time. Cool. So it is, again, a rate of change. Okay. So kind of nice, we can just take our constant acceleration formulas from what we've used before, translational, these are our kinematics formulas that we've talked about before, and rewrite them for rotational quantities. So wherever we have a translational quantity, we'll just replace it with the corresponding rotational. So instead of position in meters, we measure position in radians. So our final radian measurement is our initial, plus our initial angular velocity times time, plus 1/2 alpha t squared. And I forgot a t over here. Our next formula is final angular velocity equals initial plus angular acceleration times time. And then our third formula is final angular velocity squared equals initial squared plus 2 times alpha times my change in angle. So now let's relate linear acceleration to angular acceleration. Okay, so that's our A, we're going to relate it to alpha. We've related a couple of other translational to rotational quantities already. We have an arc length, which is in meters, is going to be our radius times our angle. Our angular velocity is the radius times our angular velocity. So those are two things that we've already talked about. So let's talk about kind of the same idea, but with acceleration. So let's say I've got something that's rotating. So let's say we've got a disk that's rotating in this direction around some central point. And let's pick a point on this rotating object. So if we're accelerating, we have some angular acceleration. Let's say we're speeding up. This point right here is also speeding up linearly. And it's going to be along a tangential path. So if you think about if you were to follow this point around as it rotates, at this point in time, the acceleration is going to be tangential to the path. So we're going to call that A tangential. Following the same kind of pattern with our other linear quantities, we're just going to take our radius and multiply by our angular quantity. So the tangential acceleration is just r times alpha. But if you look here, this point is actually making a circle. And for things that make circles, they have to have centripetal acceleration as well. So if this point was like a bug holding on to this turntable, it's going to have to accelerate inward with centripetal acceleration. So our centripetal acceleration, back from unit 3, is v squared over r. But since we're in rotational world, we're going to replace that v with r omega. So our centripetal acceleration is omega squared r squared over r. One of those r's cancels out. And so that is a formula that we can use to figure out the centripetal as well as the tangential acceleration. All right, so example time. We've got our centrifuge that accelerates from rest. So that's our initial angular velocity is 0 to 21 radians per second in 30 seconds. Our angular acceleration is just our change in velocity over change in time. So that's 2100 over 30, which is 70 radians per second squared. What is the angle, theta, that the centrifuge rotates through? I'm going to use that second equation because I know all of these other quantities. We start from 0. That's kind of a good thing to assume. We start from rest, so that goes to 0. So our angle is just going to be 1/2 times 70 times 30 squared, which is a lot of radians. It's 31,500 radians. If the radius is 5 centimeters, what is the tangential acceleration? So the tangential acceleration is just r times alpha. The radius is 5 centimeters, so 0.05 meters, times 70 is 3.5 meters per second squared. All right, moving on. We're going to talk about torque now. So we're going to get into how do forces relate to rotation. Okay. So kind of a thought experiment here. Imagine opening a big heavy door. So this right here is the hinge or the axis. And we're trying to open the door. So this is looking at it from above. Okay. So we've got force 1, force 2, and force 3. Okay. So think about if you pushed on a big heavy door, which of these forces would be the most ideal place to push on the door if you wanted to open it? It's probably going to be this one out here because it's going to take less force to open the door out here than in here. This is going to take a lot more force to open the door. And the reason for that is because this distance from the axis is smaller compared to this distance right here. So even if you push on the door with the same force but at different locations, it's going to do something different. And then if you think about someone out here at this force 3 location pushing into the door, they're not going to open the door. As hard as they push here, it's not going to open, so it's not going to cause a rotation. So the idea behind this is just to show you that different forces do different things when we talk about rotating an object. So that idea is torque. So to cause a rotation, a torque is needed. Torque depends both on force and distance from the axis of rotation. So again, these two forces can do different things depending on how far they are from the axis. That distance is called the moment arm. Okay. But as we saw out here, force 3, which is the same distance away, does not open the door. So only the perpendicular component of force can cause a torque. Force 3 up here, this is parallel to the moment arm. Force 2 is perpendicular, so it's going to be a lot more effective in opening the door. Okay. So let's give a couple of equations now. So actually let me get a new slide. Oops. Okay, sorry about this. Clear out this. All right, so our equations for torque. Again, they depend on both distance and direction of the force. So if this is my my center of rotation here, and let's say I push with an angled force at some angle. That distance that we apply the force is r, it's the moment arm. And only the perpendicular component, so it's only going to be this component that's pushing into the door, not this component that's pushing along the axis. So it's only going to be that F sine theta. That's going to be my perpendicular component. So to calculate torque, we get a new letter. This is the Greek letter tau. Equals R times F, just that perpendicular component, or we can do R times F sine theta. And these are all vectors. Okay. All right, our unit is going to be a Newton times a meter. So nothing too fancy there. Yeah, so let's talk about the direction. Okay. So the direction of torque is along the axis of rotation. Okay. So again, if we think about something that, I'm going to kind of look at a disc rotating from the side here. So let's say we're rotating in this direction. This axis is going to be the direction of torque. So if you imagine like there's an axis here along which this object is spinning. It's going to be a little bit different than what we've talked about before with our axes. So for this object here, let's say like, I don't know, this could be your y-axis and this could be your x-axis. But then we have another axis, it's going to be the z-axis. So we have to think in 3 dimensions now. So to determine the direction of torque, we're going to use the right-hand rule. So the right-hand rule, we're going to curl our fingers in the direction of the rotation. This is specifically with your right hand. And your thumb is going to equal the direction of the torque. So if I imagine I'm going to take my hand and I'm going to curl my fingers in the direction of this rotation. And then your thumb is going to point in the direction of the torque. So for this object here, the torque is pointing kind of out of the disc in the positive z direction. And that just gives us a set of conventions to use. Typically, we're going to say counterclockwise is positive. So counterclockwise is opposite of a clock. And then clockwise is going to be negative. That'll be this direction. Cool. And then the last big idea, weight. We're going to always assume that weight acts at the center of mass of an object. Because a lot of times weight is going to maybe apply a torque. We're just always going to draw it right in the middle of the object. So for example, we have a 2-meter long bar can rotate about a fixed end. We have a vertical force applied at this end. The weight, I'm going to assume, acts at this end, or in the middle. So we've got some applied force keeping it from rotating, because it wants to swing and rotate because of this downward force here. But I want to know, how big does this force have to be in order to hold the bar up, keep it from swinging? So I know that the weight over here acts 1 meter away, and this applied force is out here at 2 meters. So remember, distance also affects torque. Right here, we are at equilibrium. We're going to call that static equilibrium. So what that means is if I add up all the torques, they're going to equal 0. And that's because we're not rotating. So I'm going to go ahead and look at from this point A here, so the sum of torque around point A is going to be 0. If I use my right-hand rule, looks like this weight is going to cause a clockwise rotation if that was the only force. So that's going to be negative. So negative Fg times 1 meter plus, this would cause a counterclockwise rotation, that applied force times 2 meters. So to simplify that, I've just got negative Fg plus 2F. We're trying to figure out how large must F be, so let's rearrange this, add Fg to the other side, and then divide by 2. It looks like that force applied at the end